Quantum information processing is based on quantum mechanics. So in this very first chapter, we are going to look at the foundations of this theory, first starting from the most general principles and then working our way towards the systems that we are interested in. These general principles can be broken into 4 parts concerning the states of a quantum system. The observables that you encounter, the dynamics of the system, and measurements. We are going to use the Dirac notation, in which we denote the states by the symbol here with this vertical line, the name of the state and this angular bracket. And mathematically, these will be elements of a Hilbert space. A Hilbert space is a vector space with a scalar product, and it is complete in a certain sense, similar to how the real numbers complete the rational numbers. And I will, of course, explain what all of this means now. The fact that this is a vector space simply means that we have the superposition principle. So if we have 2 states, psi and phi, then we can combine them into a new state, including some possibly complex coefficients. So this will also be an element of this Hilbert space. And we are going actually in this Dirac notation denote these states very concisely, just as a reminder of how we obtained them in this way here. So this is the most general manifestation of the superposition principle, which can boil down to wave-like features in many systems. So this is the vector nature of this space. The vector space basically has these linear features. The Hilbert space also has a scalar product, so there is simply a prescription to take 2 states and combine them and get a complex number out of this. So in Dirac notation, we are going to write this like this. And this is simply going to be a complex number. And again, this is obeying some linear features. So for instance, if you multiply out a product such as this, psi a phi plus b chi, then you can break this down into different parts. So you can simply multiply everything out. And then there are 2 more rules for this, which specify what happens when we interchange the 2 entries. Then you just get the complex conjugate. And there's also a rule that this can be used to measure the length of these states. So this is generally going to give you a positive real number. It's only going to be 0 if we are dealing with the so-called 0 state or 0 vector. So that in this vector space, we will have one particular state that doesn't do anything. I'm going to denote this with this little stroke here. So this is going to be our 0 vector. And so only for the 0 vector, so this equality only applies for the 0 vector. Only the 0 vector will be of 0 length. Okay, so these are the main features of the scalar product and of the vector space. Now, one of the nice things of the Dirac notation is that it contains a magic rule, and that involves a state which is with an angular bracket pointing into the other direction. So this we are going to call the dual states, and they live in the dual Hilbert space. And they're basically just like the left-hand side of these scalar products. So whenever we are going to meet a product such as this between a dual state and a normal state, then we are going to replace this by the scalar product. And this is a truly magical rule because it simplifies a lot of the calculations in this framework. Now, if you look at this rule here, this actually implies that if you work out these rules here, but with a superposition in the first entry, then you have to be a little bit careful because you encounter some complex conjugations of the scalars that appear in here. And this simply translates to something for the dual state. So we can simply remember always this rule here, that if you take a state and you multiply it by a number and then you make the dual state out of this, then you can still pull this number to the front, similar to the rules that we have up here. But you would have to do it with a complex conjugation. This covers 2 of the 3 central features of a Hilbert space. The third one was the completeness, and this simply means that we can introduce a basis in which we can carry out our calculations. That seems to be something like a given if you think of a finite Hilbert space, say a vector in a certain finite dimensional space, and you introduce something like Cartesian coordinates. These Hilbert spaces in principle could be infinitely dimensional, but they actually will not be in our setting. I nonetheless want to lay down the general features here, so I'm going to explain what this means as well. We are certainly going to use a very specific basis, what we are going to call the computational basis. So it's really worthwhile thinking of what a basis actually means in the most general sense. So we can introduce a basis, and this will simply be a set of states, so that we can write all the other states as a superposition of those. So any kind of state can be written as a superposition with some coefficients psi n running over all of these states. And I'm going just to assume for the moment that this is a discrete set of states. It could also be a continuous set of states, at least partially, and then some of the sum would be replaced by an integral, or maybe all of the sum would be replaced by an integral. Having the scalar product, we can introduce some very useful notions. And the first one is of a normalized state. That's simply a state which has a unit length. So what we are going to say is that the scalar product of a state with itself is actually the square of the length. And then there are particular states which have a unit length, and these we call normalized. And then secondly, when we have 2 states for which the scalar product vanishes, then we call these orthogonal. And what we are going to assume when we talk about this basis is that these are so-called orthogonal normalized bases, or we call them also an orthonormal basis. So we are going to assume that the scalar product between 2 states in the basis vanishes when we talk about 2 different states. And if we talk about the same state, then this is just a normalized state. So this is like our basis in Cartesian coordinates. And in such a basis, then these coefficients psi n can be simply obtained by the scalar product of a basis state with the state that we are interested to analyze in this way. Now, working in this basis, we can then actually work out what the scalar product is. If you now take 2 states, psi and phi, and the expansion coefficients of phi are just defined in the same way as for psi, then you can work out how the scalar product looks like in this basis. And then you get the following expression, which is just a sum over all the coefficients, where you have the same indices on both entries and a complex conjugation on the first one. And you can actually write this in a normal vector notation as a product between a row vector and a column vector, where the row vector includes this complex conjugation. So you actually obtain this from the column vector of the state by a so-called Hermitian conjugation, which I denote by this dagger here. For us, the completeness of these Hilbert spaces will be a given, simply because they have a finite dimension in our settings. But it can actually be expressed also in a very compact way, which I'm going to prepare here. But I'm only going to complete the statement about completeness when we have introduced operators, which is our next step. Observables in quantum systems are linear Hermitian operators. Linear Hermitian operators. And I'm going to denote them by a symbol like A with a little hat on top of it. A hat really indicates that this is not just a number, but it is a slightly more complex object, but actually not that complex. And now I have to explain all the three terms again. So there are again three key features. The first one being an operator simply means that it takes a state and makes a new state out of this, which I'm going to denote in this Dirac notation, just again analogous to what we did here, by just reminding us of how we obtained the state. And this is supposed to be a state in the Hilbert space. Secondly, these operators are linear, which means if we act on a superposition, then we can again multiply out all terms in the most natural way. And thirdly, Hermitian is a certain class of operators, so that if you take any kind of scalar product between two states, such as this one, this should give you the same result as applying this operator to the other entry in the scalar product. What you would normally have is there would always be an operator defined so that this is always true and you denote it by a dagger. So this would always be true if you just stick in another operator at this place, which you call a dagger. And therefore, this really means that a dagger is the same as a. So you can look at this as a definition. So this is a definition of the Hermitian conjugated operator. And we just want to have these two to be the same. We are going to encounter a different important class of operators in just a second, the so-called unitary operators. And so this general definition which I give here is a very useful one. Now let me come back to the completeness. There is a very simple operator, which I'm going to put up here, the so-called identity operator, which is not going to do anything to our state. And our completeness can be expressed by writing this identity operator in the following form, in such an orthonormal basis. And this will imply that we don't miss out any states. And then, for instance, we can obtain the rule given up here simply by looking at this condition. And I leave this as a little exercise. So this completeness condition will be very useful for us simply because it simplifies some of our derivations. If you do this little exercise, you will see why this is actually also an operator. And this is simply down to our rule here, this rule here. Whenever we multiply such a combination of symbols with a state, we will encounter this product, and therefore we will get a state out of this. And this is something that you should really have a look at yourself to see how this works in practice. Okay, so this is the completeness condition. Now we can, of course, formulate all our operators also in this basis, and in particular, so in an orthonormal basis, we can write an operator A such as this. And these matrix elements, as they are called A and M, are simply obtained again from a scalar product, but now with the operator wedged into the middle of it. So this again applies to an orthogonal normalized basis. Now there is a very important link between states and observables or operators, and this concerns the eigenvalues and the eigenvectors or eigenstates of these operators. So this is defined in the following way, that for any operator A, there is a particular set of states, which I'm going to denote as AN, so that if you apply the operator to the state, you get the same state back, just multiplied by a number, which I call AN as well. These particular states, which are special for any kind of operator, are called the eigenvectors or eigenstates in a physical context. And these numbers here, they are called the eigenvalues. Now, Hermitian operators are special because the eigenvalues are real. And if you look at two different eigenstates with different eigenvalues, then they are orthogonal to each other. And this means that we can use all these eigenstates and form a complete basis out of them. And we can also normalize this basis. Now, using this special basis, this so-called eigenbasis, you can write the operator in a very compact form, namely in a so-called diagonal form. So in contrast to the case up here, where we have two different pairs of states in every product, we here just have the same state in these products. And finally, concerning these operators, just as we can compare states by the scalar product, we can compare the operators by the so-called commutator, which is defined in the following way. A, B, commutator is just looking at the difference of applying these operators in opposite order. And this is an operator in itself. The product of two operators is simply defined by applying them consecutively. And the difference of operators is simply defined by first working out what the operators are doing on states and then taking the difference of these results. And now there are very special pairs of operators for which this commutator vanishes. So if this becomes the so-called zero operator, then we have a very special pair of states. The zero operator is simply defined to take any state and give you the zero state out of this, the state which I've defined up here. If this is the case, then we call the associated observables simultaneous observables. And mathematically, this means that they have the same eigenstates or eigenvectors. So if we write them in this diagonal form, the only difference would be in the eigenvalues. So these are the main features of observables of quantum systems, expressed as mathematical features of operators. Now, the dynamics of quantum systems will be very important in this course because we want to manipulate quantum systems over time and indeed interpret this as the manipulation of information. And very generally, this is generated by a very special observable, the so-called Hamiltonian, which indeed can depend on time. And time is a parameter in here, is a real number. There's no observable for time in quantum mechanics. It serves as a parameter. And this means that all the states are also parameterized by this parameter time. And in order to figure out how they change over time, we have the so-called Schrödinger equation, which just looks like this. Now, the Hamiltonian is an observable. It is actually the observable for energy. And this means it is a Hermitian linear operator, and this has consequences for the time evolution. It means that if we look at the connection between a state at time, say 0, and a later time t, then first of all, there will be a linear relation between the two. And this is given by the so-called unitary time evolution operator. And this is indeed a special class of operators, unitary operators. So this is a time evolution operator. Now, unitary operators are again a certain class of operators, and they're again defined by a certain property of the scalar product. Namely, if you insert these operators into the scalar product, into both entries null, then nothing is going to change. So this defines unitary operators. Again, they can also be characterized in terms of their eigenvalues and eigenstates. The eigenstates are again orthogonal if you talk about eigenvalues which have different values. And the eigenvalues themselves are now complex numbers of unit length, so-called unimodular numbers. So we can again write these operators in this diagonal form, but the eigenvalues would now just not be real numbers, but they would be complex numbers of unit length. Now we are often going to look at systems in which the Hamiltonian does not change over time, at least for a certain interval, the interval that we're interested in this time evolution. And then we can, instead of solving this time-dependent Schrödinger equation, also solve the so-called stationary Schrödinger equation. And then we can write the solutions of the time-dependent Schrödinger equation in terms of these states. And we can also write the unitary time evolution operator in terms of these states. But in particular, we have a very shorthand notation for this solution. In that case, we can write u as e to the minus IHT divided by h bar. So this applies to this particular situation where there is no time dependence in the Hamiltonian. Finally, we come to measurements, which is really the postulate that ties everything together. And this in itself has several parts. So first of all, any measurement concerns a physical observable. So to any measurement apparatus, you can assign a Hamiltonian operator A. And then the outcomes, the values that you can read off of your apparatus, are restricted to the eigenvalues of this operator A. So this is a source of quantization of observable properties such as energy in the bound state, for example. These will be real numbers because these observables are Hermitian operators. Secondly, these outcomes occur with probabilities. That's of course a key ingredient of quantum mechanics. So the probability that our outcome A is equal to one of these eigenvalues is given by scalar product between the quantum state at the time of the measurement and the eigenstate associated to this eigenvalue here. So this is a state that appears in this relation up here. So this gives us a complex number, and we have to take the absolute value squared of this. This assumes that our quantum state is normalized, because then our probabilities will also be normalized. Now it is of course possible that for any given eigenvalue and therefore measurement outcome, there are actually several eigenstates. That's something that we call degeneracy. And in this case, we simply need to sum over all the states which have the correct eigenvalue. Now this can be expressed quite neatly in the following compact form, involving a scalar product and something which we call a projection operator. So this is the projection operator, and I'm going to denote it as PA with a hat. So this is an operator, and A just indicates the eigenvalue which we are concerned with. Now there's a third important element of these measurements, namely after the measurement your state has changed. So there is an effect of the measurement on your quantum system, and it changes in a very particular and drastic way, namely it forces the state into one of these eigenstates, exactly into the eigenstate of the observed value that you have obtained. So this is the effect of the measurement on your quantum system. And this, of course, again applies to the case that for any given outcome you have exactly one state. But more generally, this actually is reading as a projection, just with this projection operator A. This will be important for us because we will read out information from different parts of your quantum system, and therefore actually do sort of incomplete measurements looking at certain observables that only concern some part of the information in our quantum system. So this gives you your post-measurement state, which I'm going to call psi A. You can then actually also obtain the probabilities simply from the length of these states. In here, we have not yet normalized our states, and we can write it like this. And finally, we can condense all of this information into very useful numbers, which are the expectation values. And they're simply obtained in this following form, just as a scalar product with this operator inserted into the middle. And this is really just like the average of these outcomes defined in the standard way. In this course, we will use these elements in the following way. The quantum states help us to encode information in the quantum system, and the observables help us to read out this information in measurements. And in terms of how these observables enter the Hamiltonian, they also tell us how we can manipulate the quantum information in the system. Let us next look at some examples to see how this works in practice. I will start with a very familiar setting, that of a point particle in one dimensions, and then we work towards the setting that we are applying in this course, which are made out of the most simplest quantum systems with just two states. And then we build them up into more complex systems by just composing them into a larger system.